Right, so this is the lecture plan for today's um, class. We are going to first talk about quantization, pruning, and then like talk about some of these optimizations for large language model serving systems. So first, let's talk about quantization, and let's see how is that different from traditional quantization. A quick review. So quantization, you are lowering the bit width and improve the efficiency, right? You're mapping from a floating point number to a integer numbers or even to binary numbers. Naive quantization methods are not performing very well. So weight. So this W8 A8 means that weight integer 8, activation integer 8. Quantization has been an industrial standard for CNNs, but not for large language models. Why? And this one, shows you, the performance drop. So when you are simply apply non-uniform quantization for all activations and the weights, the accuracy just drops significantly. Um, Other than the smooth quant, which is the idea we are going to introduce, and you can see that the smooth quant like it's very close to the baseline. Okay. So the reason is that systematic outliers emerge in activations when we scale up a large language model beyond 6.7 billion. And traditional CNN quantization methods will destroy the accuracy. Why? What does that mean? So this is the key figure to show what's the problem. So let's first look at the right-hand side. Give me one sec. Let me try to pull up the laser pointer again. The right-hand side over here, you can see that, well, this is the input channel, this is the output channel, and the z-axis is the value, right? And you can see that they are relatively flat. It means that the value of the weights, they are not like varying significantly. Um, they could be like, the range is relatively small. But the interesting thing about the activation is that you can see that, if you look at this axis, let's say this is x, this is the x-axis is the token, the y-axis is the dimension, the the um the vector dimension. The interesting thing you can see that for some of these dimensions, um, the the values are significantly higher than the other, all these blue numbers. Okay. And what is the problem with all these outliers if you just uniformly apply, activation integer 8? Because these values are so big and you are trying to map this whole thing into, the integer range, then all these other blue numbers will just becomes like almost to zero, right? Because they are so compressed. Does that make sense? So therefore, like a lot of information is going to be lost. You just uniformly compress like everything into integer 8. Um, but also luckily, all these outliers we observed that they usually appears in a fixed number of channels. By channel, we mean the particular dimensions in the vector. Okay, so these outliers are positioned in these channels. So we can do some, handle somehow we can handle them in a way to so that like when we are compressing these outliers, we don't squash all these rest of blue numbers, almost to zero. So that's kind of the idea. So the smooth quant idea is trying to migrate the quantization difficulty. The idea is, this one, the outlier is so big, the maximum number and smaller number are so big. Can we somehow, and that's difficult to quantize, can we somehow migrate that difficultiness into the weight? But the question is how, right? So how? The idea is quite interesting. So the main idea is that let me first use a quick example to show you what's the idea. So let's say like the activation matrix is this. So 1, 16, 2, 6, 2, 8, 1, 9. Okay. So that's the activation. And the weight it's 2 1 2. Well, I'm going to discard the signs 1 1 1 2 1 2. So you can see that the activation this one gives you the idea is that in the activation some of the dimensions you can see that they are particularly large than the rest of the numbers, right? And for the weight, all these numbers they are kind of like confined into a fixed range. Okay, so instead of I'm trying to quantize this x itself, I'm going to do some transformation. I'm going to divide. I'm going to divide this 16 by 4 and this 8 as well by 4. What that may give you is that like this number is going to be -4 and 2. So for the 6 and the 9, I'm going to divide it by 3. Okay, so give you 2 and the 3. Okay, but if you are dividing these two numbers by a factor, but what the problem is that now the output of these two matrices is no longer be correct, right? Because you divide all these the whole channel by a factor. And in order to save the output activation value, what we can do, a smart thing that we can do is that we can multiply the corresponding rows in the weighted matrix by the same scaling factor, let's say 4. Okay, so this column divided by 4, and then this corresponding row is going to be multiplied by 4. This column divided by 3, so this corresponding row is going to be multiplied by 3. In this way, we get these two transformed matrix. So this one now, see, the largest value now becomes the largest absolute value becomes 4 and 1. So the range is much smaller, right? And this one, when you are scale up all these weights now, also it's 4 to 1. So they are kind of in similar range. Now, if you are applying, let's say, weight A activation 8, this one will give you much better quantization results. And this transformation doesn't change the activation value at all, right? Because by multiplying and dividing the same factor, the final activation value will stay the same. Does that make sense? So by doing this, this is the core idea of this smooth quant. Okay. But now the question is that how do you know, I need to divide it by 4? How do you know I need to divide it by 3, right? So the scaling factor, they are using, this equation here. So let's see, use an example to show you. So for this input activation X, okay, first we are going to get the max of absolute value of X. So give you this, 16, right? And then I'm going to also get the absolute max for the weight matrix, which is essentially is 2, okay? Though the scaling factor is calculated by square root of 16 divided by 2, which is, I'm sorry, 16 divided by 2, wait one sec. I'm sorry. So, it's divide. It's actually it should be square root of 16 divided by square root. Hey, wait. I'm sorry. So this I'm sorry. So it's the 16 divided by 1, which is 16, and square root gets you the 4. And this is 9 divided 1, square root gives you 3, 2 by 2 give you 1, 2 by 2 give you 1. So now you get this number. So the 4 is the scaling factor for this column, and the 3 is for this column. So that's how they get the scaling factor. Here we are assume the alpha here is 0 0.5, so which give you the square root. But this one doesn't have to be 0 0.5. Okay, so let's say like for now, let's just assume the alpha is 0 0.5, and it'll give you 4 and the 3. And then like the new equation essentially by doing this, you got dividing by this, and this one is going to multiply by this, get the new matrix. And the new matrix, the new activation matrix and the new weight matrix actually is going to give you this exactly same activation value as the old value. Okay. During the inference time, it's nothing need to be changed, right? So you just do the calculation, give you the exact same activation output. Okay. So this figure is trying to do ablation study on this migration strength. So this migration strength alpha, like the example we just saw was 0 0.5, right? It controls the amount of quantization difficulty migrated from activation to weight. Why? Why? If the alpha is small, okay, then the scaling factor will be small, right? Then the activation will be there will be less activation hardness, difficultiness being migrated to the weight matrix. Does that make sense? Therefore, if alpha is small, the activation will be hard. Let's go to the extreme. Let's say like alpha is 0. What that means is that we are not doing any migration, right? So the activation is still itself, and the weight is still itself. So that's the original one. So it's going to be harder. Uh, and then like if you are migrating too much, now like activation becomes easier, but the weight becomes harder. So there is a sweet point spot for the value of the migration strength to find a good a good alpha number to do this smooth quant. So smooth quant is accurate and efficient. It well maintains the accuracy without fine tuning. Can both accelerate the inference and have a smaller memory footprint. So this one can basically give you the accuracy. So this is accuracy compared to floating point for all these different models, the OPT, Broom and GLM. See, it's even give you a little bit for this one, even give you a little bit higher accuracy. And this one shows the latency. Smooth quant give you smaller latency and give smaller memory. That means that like you can use fewer GPUs and less memory to give you similar accuracy. And this one also like scales up to 530B for the accuracy and efficiency. You can see that still like maintains really good accuracy. This one even give you higher accuracy. This is a little bit lower. This one give you higher. Okay, so average accuracy is actually the same with fewer GPU and the memory. So llama, they applied this smooth quant to llama. So give you a big llama to smaller llama. And also like it shows the perplexity, I think. Comparison, you can see that you're only increasing, it's only increasing the perplexity by just a little tiny bit. So smooth quant, it's one. So next, I want to talk about this weight-only quantization, this AWQ, and the tiny chat. So far, the smooth quant for the smooth quant, what we talked about is that we intended for all these large language model we've been talking about is we're assuming it's batch serving. means that like we have a good set of data ready, and we give it to the model, and the model is going to, surface it. But if you think about a different application scenario, which is the robot, okay? So if the large language model is running on the robot, you are not giving a whole bunch of data to the robot all at once, right? Or it's not possible that like many people are sending requests simultaneously to this robot. Usually it's a one-to-one interaction. You give like say, oh, here's the credit card, here charge it, right? So that's one request. So when you are just doing this single query large language model inference, the math is a little bit different. What does that mean? When you only have one inquiry come to the system, which is here it says like the batch size is one versus the batch size of 128. Because when the batch size is one, the computation is relatively low, right? Compared to, if I have like a batch size of 128. So the computation is relatively small. And what does that mean? What that means is that now the GPU is going to do all this computation running very hard. But it finished the task really quick because I only have one batch to calculate. Then the majority of the time, it's going to sit there to wait for the model to load all those KV cache from the memory. Right. So the wait becomes the bottleneck. The computation is not. Okay. So therefore, in this setting, we need to a lower bit weight, because if you have a lower bit weight, I can grab the data much faster, right? But the activation doesn't really matter because now I only have one batch of input. Okay, so therefore, in this single batch serving scenario, which is all these mobile, edge, robot, a different kind of activation method is needed. So they propose this wait for activation 16, which means that the wait is in integer 4 and activation remains the floating point 16 bit. Okay, and let's see how that plays out. So it says low bit wait quantization. The wait loading is the efficiency bottleneck for edge inferences. This one give you this breakdown of this context generation and token generation. So what that means is, I think I probably forgot. I think Greg asked me about this, but I did not mentioning this. So if you think about it, when we are using a large language model, when you are entering all your prompt to the model, there are actually two phases. The first phase is called this pre-filling or this context stage. What that means is that, well, now I have all the tokens, and I'm going to do all those self attention, blah blah, and all that. I can actually process all these prompt tokens in parallel. Does that make sense? Because now I have everything, right? But once you process all these prompt tokens and generate the first token, okay, now I need to use the first token plus the prompt to generate the second token, right? So this is autoregressive process. So now like every time I'm generating a new token, I need to use like all the prompt token as well as the token I just generated. So that's the generation process, the stage. So these two different stage. So in the first stage, because we only have all these prompts, I can process all these prompt tokens in parallel. I can process all those tokens very fast. But in the subsequent generation stage, like I need to generate token one by one. Basically, it's going to be much slower. Okay, so in this generation stage is bounded by memory bandwidth because I need to get all these weights and all these KV cache. Okay, so that's kind of the main idea. So under this scenario, in this edge inference, the activation, the weight is going to be more expensive to load. So this one actually shows you, the size of the weight compared to the activation for both the attention stage, attention layer, as well as the fully connected layer. Okay, so the idea is that, so the takeaway is that weight is more expensive to load. Um, so they propose this AWQ, the activation aware quantization. So target group-wise low bit with only activation. So well, if we simply just round everything to the nearest, if you just simply round everything to the nearest value, you get this this quantized weight from floating point 16 to integer 3. Then you will see, like, the perplexity just increases significantly. So which means that the generation performance is bad, right? Um, so but if you then people like see why. So if you remember, like in this activation, and people find that all these weights, they are not equally created equal. Okay, if for example for this yellow channel, I'm maintaining this original precision, and the rest of them got quantized. Okay, and the perplexity suddenly dropped significantly. Why is that? Why is that? If you still remember the model I showed here, if you still remember the model I showed here, when you are quantize the weight, if you just uniformly quantize everything, the performance just drops. But if you, for some of the channels, which channels? Well, if you look at the image, it's quite intuitive actually. If the channels that's corresponding out to these outer layers, right? Corresponding to these outer layers, they are kept relatively good. Then the model accuracy actually got maintained because those values apparently are more important than the rest of them, right? So therefore, people find that, well, for some of the weighted channels, if we just keep them unquantized, you can significantly recover the accuracy. But if you do this, there's one issue, is that the weight matrix now consists of a bunch of integers, as well as like just several rows of floating point numbers. And the GPUs are not designed in a way to handle this, right? So what do we do? Oh, actually, before we talk about that, the question is, how do we select all these important channels, right? Um, uh, uh, a simple idea is that you just select these channels based on the weight. But I already showed you that's not the best idea. You actually need to be aware of this activation value, because if the activation value is very high, then uh, you probably shouldn't quantize that channel, right? So that's the key idea. So the activation value, okay, is going to determine which channels should not be quantized. However, it's really not is it really necessary to introduce mixed precision? The more important is like the system usually are not very good in handling these kind of um, not good in handling these kind of mixed precision calculations. So that will introduce extra overhead in conversion and all that. So while to fix that problem, well, this one actually give you this more mathematical way on quantize how do you quantize this. Um, so when we are introducing, if we were introducing this mix, I'm sorry, the floating point number in this channel, then like it's going to be really hard to calculate. So how to fix this? How to fix this? Um, um, they propose a very interesting and counterintuitive idea. So, well, if I have to, if I have to keep the um I want to maintain the accuracy for this weight. Okay, I want to maintain this. So, is there a way that like I'm using integer, but without sacrificing too much of accuracy? In order to answer that question, let's first take a look. When you have a bunch of number as negative 2.5, negative 3.5, plus a positive 1.9, 1.4, when you are quantize this number to the nearest integer, what is the quantization error? Let's first take a look at 1.9. So if you have a 1.9, the quantization error is 0. If you round this to 2, so then there's a quantization error of 0.1, right? 0.1. 0.1 out of 1.9. So that's how much log error you are introducing to this value. Then like if you look at this 2.5, um, if we round this to 3, okay? So the quantization error is going to be 0.5. So you are introducing 0.5 error to a value 2.5. Basically, you are introducing like 20%. You are changing the value by 20%. Does that make sense? For this one, it's the same. 0.6. If you round this to 1, right? So you are essentially removing 40% of the value. Does that make sense? Which is not great, and that's introduced a lot of error basically. So the AWQ, the core idea of AWQ is this. I'm going to scale this row here. Okay. Let's see, do I have a pen here? Yes. I'm going to scale up this whole row here. Let's say I'm going to multiply this scaling factor 4. Okay. And then this row now becomes negative 10, right? Negative 14. Okay. And this one is going to be 7.6. Okay. And then this one going to be 6.6, 5.6. Does that make sense? Does that make sense? By multiplying a scaling factor 4, now if I quantize this 10 to the closest, I'm actually sacrificing 0. Okay? Because it's an integer number itself. This one, the error is 0. This one, the error essentially is a 0.4 out of 7.6. So that's how much error I'm introducing, right? And this one is 0.4 out of 5.6. So you can see that by multiplying a number, I'm reducing, and then I'm quantizing that to the nearest integer. I'm reducing the error I'm introducing to the system. Does that make sense? So, but remember, if you are multiplying a scaling factor to this column, you need to do what? You need to divide the same number to this. Right? You need to divide 4 for this column. So you multiply this row and you're dividing to this column. Okay? So by doing this, and remember, now what we are talking about is the activation will not be quantized. Only the weight will be quantized. So this doesn't affect the quantization difficulty of X at all because we are not quantized X at all. Okay, so by doing this, essentially we are trying to reduce the error we are introducing to the system for this thing. So so this one give you this you know um, this one basically the equation here is essentially is trying to explain what I just explained. So when you are doing that, essentially you are reduce the quantization error that's introduced to the system. Okay, so so therefore the takeaway is that the AWQ, when you are quantize the weight, even though we are not quantizing the activation, so but the quantization for the weight need to be activation aware, okay, for these important channels, and and the scaling does not always bring good. So we need to find what is the best skills, right? So now in the example, I just give you this random number four, but what is the best number scaling factor? So what essentially they are using this. Um, uh, this is linear programming. So what it does essentially says, well, for the quantized, so this is the quantized weight. This is the activation. Okay. So after doing this shifting and minus the original WX, basically we are calculating the output activation error, right? So we want to minimize the output activation error. So this is what we already saw this when we were talking about the quantization for CNNs, right? So so we are trying to minimize this. And basically you are trying to find it all the alpha value that give you the lowest activation error. So there's a linear program to try to find to search the alpha. So once you have the alpha, then you have the scaling factor S. Okay, so that's kind of the idea. So the search objective is the mean square root error for the activation for the output. So this is the input activation, this is the weight, and this is the output activation. So we are trying to minimize the output activation error over here. Right. So advantages of AWQ, it's accurate, simple, easy to implement, less depend. So they did some comparison. They need less. After you do this AWQ, they need to do less um, less instruction tune the model and all that. You need a less calibration data set. Where's it? Oh, it's less dependent on the calibration data set. This one give you the comparison. So this is the perplexity. So this is a AWQ here over here. Okay. And for different model size llama 2 llama. And you can see that for AWQ, the perplexity, this is a round to nearest. This is GPTQ. Okay. So you can see that it gives you quite good performance. So AWQ also works for visual language model. So like they tried a POM-E-like architecture and augment the large language model. This is what we talked about in the previous lecture, right? So and they find that the AWQ also works really well for VRMs. Can see that like please tell me what's happening in the video. The video shows a soccer game where a player scores a goal. The crowd cheers as the player celebrates with his teammates. And this one shows you the the quantization of a multi-model this VRMs. Okay, so this one gives you AWQ to int 4. Okay, and these are different data sets, and you can see that the perplexity actually. I'm sorry, is this accurate? I think this probably is the accuracy. So it's only dropped a little bit, the average. Then like they also introduced this tiny chat for edge inferences. Okay. The reason is that like with with if you think about if we are doing a integer a weight, so activation is a 16, okay? And the integer, I'm sorry, the weight is integer 4, right? And then you need to do the this. Um, so what a tiny chat is trying to solve is that, well, when you have this, when you are store the numbers like this 4-bit integers, usually we are still like store them in memory in words, right? So we know like each word is 32-bit. So you probably can like pack eight, like a total of eight 4-bit number into one word, right? So but like when you are trying to do all these multiplication for a floating point 16 with an integer 4, it doesn't work directly because the GPU is not just not designed in this way, right? So the all these weights need to be taken out, okay? To be get from the memory, need to be unpacked, okay? So I need to unpack all these. Basically, I need to extract all these numbers out, okay? After you do, if you after you extracting them, you need to convert them back to floating point 16 so that you can multiply with this floating point 16, right? And why we're converting back? Because remember, we talked about in this single batch inference, the computation is not the bottleneck or the memory access is. So we so because the computation is not a bottleneck, so we will just uh, revert them back to 16, so to kind of like trying to maintain the accuracy here. So therefore, like how to store them, how to unpack them, how to convert them back, you all need something like to help you with the process. That's what the tiny chat is doing. So let me show you what that is. So one technique in tiny chat is this hardware aware packing. So if you were like this weight, right? If you were having this weight, and you have this each weight is a 4-bit. Okay. Now I have, oh, this is actually quite long word. So that's fine. So each cell here is a 4-bit. I have so many weights. Um, if I'm asking you right now to write a code to extract these numbers, the simplest way, I taught this in my microcontroller class, is that you can just XOR with a mask, right? So you mask and then shift it out. And you need to do this for every weight packed in this in here. Okay. So what this paper Tiny Chat does is that basically it's doing this interleaving packing. Okay. It's doing this interleaving packing. So 31, 15, 30, 14. Okay. And then like it's using a mask as 0, 0F, 0F, 0F. Okay. And then in order to get like all these W15 and all these to this, you are simply XOR, I'm sorry, and the mask with the weight. Now you directly extract all these numbers out, and they are separated by all these zeros, right? And for all these red weights, I'm going to shift it by 4 and end with the mask. Now you got all this. So basically they did this trick to kind of speed up the extraction process. They also did something, this kernel fusion. So this is a kernel fusion thing. So remember, like in this attention, we have this K and the V calculating the attention map, doing the softmax, and then like doing the calculation with the value matrix, right? So they kind of like did this system level optimization. So what did is that like for the so in GPU you have this CUDA core as well as this tensor core. Tensor core is good for all these matrix. They are just designed for matrix multiplication. Okay, and the CUDA core is more like a little bit more like CPU-like thing, which is not can be more do more logic like the conversion. Let's say like the integer 4 to floating point 16 conversion. So they did this, for each iteration, they did this weight conversion and the to this uh, floating point um, number. And then they also like using this scale and this zero number. So do this all this pre-processing got this weight. Okay, so this is so this is the conversion, and this is a revert back to the unquantization dequantization process, and you got this weight, and this matrix multiplication give you this y. They pretty much just did the system optimization that assigning all these into CUDA core and all these matrix multiplication to the tensor core. So it can significantly, accelerate the edge inference. This results shows like, the right ones give you higher throughput for all these desktop, laptop, and mobile GPUs. Also faster than the GPT-Q, llama.cpp. They even demonstrate that on this tiny device. Okay, so that's that. TinyChat also similarly supports vision that visualize this VLM vision language model, delivers like speed up and all that. Okay, so that's we talk about the smooth quant, we talk about AWQ as well as TinyChat. So next, let's talk about this QServe. So from here you can see it's activation weight 4, activation 8, and the KV4 kind of setting. And let's see why is that? So in this, in the cloud serving, most of them are weight 8, activation 8, and the KV cache also like weight. And usually now for edge serving, wait for activation 16 and KV16 is usually is better. Um, and for edge inference, as we said, like the 4 and the 16 usually it's the popular setting, and also keep the KV cache to be floating to be 16. So what QServe want to do is combine the advantage of both world. So it wants to have the weight for activation 16, give you high computation complexity, as well as give you this higher performance. So what it's trying to do is using 4-bit weight to save the memory bandwidth and using 8-bit activation to improve the peak performance. So this one shows while W8A8 is good, but W4A4 is not good because that will introduce a significant accuracy loss, cannot run efficiently. The reason is that for GPUs, they natively support weight 8, integer 8 operation, but it's not natively supporting integer 4 operation. So this one is trying to understand, the overhead when you are running the quantized matrix multiplication on GPU. Um, so if you look at the what happens for integer 8 and the wait, integer 8 wait and integer 8 activation, the computation process is something like this. So all these um, this wait and this activation, this calculation is purely done on the tensor core, right? And then the after you have all these computation, you got the output. Then like you do the conversion back to floating point, and then you do the dequantization to get the final output. So this is really good because all these all these computation intensive matrix multiplication can be all just put into the tensor core, and after you finish the computation of all these matrix multiplication, only the CUDA core only do some of the cleaning, the epilogue, some of the cleaning here, which is good. If you do integer 4 and the floating point 16 in the system on the GPU, what will happen is that you are going to do um, the conversion. You need to convert it back to floating point, and you need to dequantization, right? And then like you need to do the matrix multiplication. So basically, inside each iteration, you need to do this CUDA core computation over and over again. And the CUDA core usually are the expensive, actually, it's the expensive part. If you are repeating this CUDA core computation over and over again, this one, the performance is not going to be good. And this integer 4 and the wait and integer 4 activation, if we do both like integer 4, let's see what's happening. What is the computation happening in the GPU? So you can see that you are doing this multiplication, which is the tensor core, but then like the CUDA core need to do the conversion, the dequantization, and so again, the CUDA computation is also being repeated over and over again for each iteration. Make sense? So the takeaway is that well, W8, A8 is computationally efficient. W W4 and A16 computationally not efficient. Integer 4, wait for activation 4 computation is not efficient either. Okay, so that's kind of the takeaway. So therefore, the paper is proposing this integer wait 4 and activation 8 in order to improve the execution latency in GPU. And why this is better? Why this is better? So you only need to do the CUDA core computation, the dequantization here, and then you just tensor core, and then the CUDA core doing the result conversion and dequantization. So basically, you are moving part of it out of it. Okay. So therefore, compared to option B and option C, this option D will be, well, still going to be slower than this W8 and the activation 8, but it's going to be better than B and C. Okay. Because you are, this computation process can, the CUDA core computation is going to be out of the loop. Oh, and this one also it's not just the wait and activation because we are also going to do in the attention we are going to do the KV cache the KV attention, right? So and they also find that this this outlier in this KV weights, so they also do some smooth quant for this attention process. Okay, so this is the same as the smooth quant idea. Another optimization they did is this dequantization process. So remember when we are doing dequantization, the dequantization process is you subtract um, the a 0 point and the times a scaling factor, right? So that's how we do the dequantization. For example, like the quantizer is 7. If you subtract the this, so you got -1. I'm sorry, adding the zero, add the 0 point, and then like you got this, and then you multiply with 2, you got -2, blah blah, and all that. Um, but there is a problem with this method. So when you are adding, the original value to when you are adding original value to the 0 point, okay, um, because the 0 point usually it's a can be both negative and positive number. So they becomes all this two's complement representation, right? So when you're adding this to the 0 point, all this one becomes this negative numbers, and we use two's complement number to represent them. So what is the problem is that like now the -1 becomes FFF. So what that means is that it's all ones, right? It's a 8 1. Okay. And if you look at this 8 1, this number, then you multiply with the scaling factor. Um, because it's the largest number already, you multiply anything, it's going to be overflowing. And because we are packing, when we are packing multiple, quantize the number into this single memory location, this 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 multiplication is going to overflow to the adjacent value, which basically is going to destroy the adjacent values. Does that make sense? So this is going to destroy the adjacent values. Okay, so what they did is that they did a optimization. Um, instead of instead of adding the 0 point and multiply the scaling factor, they are multiply the number first and then adding the scaling factor. But remember here, it's the now the 0 point becomes -16y because basically now because you multiply first, then when you are subtracting the 0 point, you need to multiply this 2 and the -8. Okay, so but why this is actually helping? Why this is helping? The reason this helps is that when you are all these quantized weight, originally usually they are stored as unsigned positive number. If you multiply this number, essentially it's a shifting, right? And because you can see that even after the shifting, after multiplication, you have all these, you still have all these zeros before the number. Okay, this one doesn't. Then like when you are adding a number, it's not overflowing into this adjacent values. Okay, so in this way that we can avoid the overflow problem. So they show the results. This QServe um, shows it's faster, higher throughput. Okay, so next, so that's all these quantization techniques we talked about. Next, let me quickly talk about the pruning and the sparsity. So for pruning, the again the Wanda idea basically says, well, the just like quantization, the pruning actually should also be quantization aware. Um, what does that mean? So if we were just pruning based on the model, the magnitude of the weight, and you are going to have this, all these 0, 1, 1, 0, those are smaller numbers got pruned, right? That's a smaller value. But because of the way that in large language model the distribution of the activation is in that way, therefore this for example for this value it's 8. Therefore for the weight that's corresponding that's going to multiply with number should not be quantized, right? So we shouldn't do that. So what they did essentially it's using the activation value importance as the importance to prune. So what they did is that they, multiply the weight with matrix with the activation. So essentially, this one give you the what is the potential output activation, right? So and then based on the output value to the output activation value to group them and prune them. Okay, so in this way, I'm making sure the weight that's corresponding to this 8 is not going to be uh, uh, pruned aggressively. Right. So this is the experimental results. So deja vu is another pruning um, idea. It's this dynamic pruning. It's very similar to MOE, but works in a different way. So let me just explain this really quick. So you can see that like in deja vu, you have a something called a predictor. So when I have an input, okay, I'm going to do the attention, and meanwhile, I'm going to going through use the input to go to the predictor. The predictor is going to say, oh, which of these um, uh, blocks of the MLP computation should be used. Okay, so this is very similar to this MOE idea, right? So and then therefore only these blocks will be calculated with the attention. So that's the deja vu idea. And then like also this attention sparsity, so which is basically is token pruning and head pruning. Um, the give you this example here, like as a visual treat, the film is almost perfect. Okay, so after you go through one layer, initially I have 11 tokens and the 12 heads. After one layer, I'm going to prune some of the token and some of the heads. I end up have 5 tokens as treat, comma, film perfect. Okay. And then like 12 heads now only reduced to 10 heads. And then go through another layer and then find the 2 tokens film perfect and 8 heads finally give you the result. Okay. But then the question is, well, how do I prune these tokens, right? So the idea is this. In the self-attention process, I bet the video game is a lot of more fun than the film. Okay, and then I'm calculating all these attention score, and for each column, I'm accumulating the attention scores. Okay, so for example, like 0.4, 1.3, and this one give you 1.8, but this like pinkish 0.4. What the last row here says is that, well, for every word, how many words are paying attention to me? If like everyone is paying attention to me, means that it's important. If nobody is paying attention to me, for example, like okay, doesn't really nobody pays attention to right? There's no meaning in it. So I can just drop these tokens. So by using this accumulated attention score as the importance of the token, so we can keep dropping all these uh, all these tokens. Shufang is asking in other activation-based weight importance and the scaling determined. Yes, they are all designed off. Wait, no. So they are all designed offline. So it's based on metrics, based on the data, the offline data, and calculate. Okay, so the sparse attempt is trying to do that attempt pruning, and also like it has this V pruning. Basically, if the Q and the K value, if this value is very small, I'm not going to fetch V anyway because it's not important. It's not going to be the V is not going to be operated on. Okay, so also like talk about this progressive quantization means that I'm going to use a lower precision value to do the quantization map first. And then I'm going to do the softmax. Only if the softmax is not confident, then I'm going to fetch the high precision. Otherwise, I'm just going to use the low precision to do this attention map and softmax and all that. And also like this H2O is another idea. So the observation for H2O basically says, well, for when I'm doing the when I'm doing the attention, the most important tokens that I need to pay attention to is its local token. Basically, it's the tokens that's immediately preceding myself. So for example, like um, for this token, I'm only paying attention to the two tokens before me. Okay, so those are two tokens important, as well as heavy hitter tokens. What does that mean? Means that like some of the tokens are kept being attention to. Those are may not be immediately before me, right? So this is kind of like a cache idea. So I'm going to keep the immediate two or three tokens before me, as well as some of the important tokens like long before me. But how do you calculate? But how do you calculate like which tokens are the heavy hitters? So the idea is this. So for they keep a cache over here, like child left and the plate. Okay, and then for each query, you are going to get a attention score, right? For these cached tokens. Okay, so you are maintaining a table to keep the score for each token in the cache, and then you just accumulate all these. Okay, a couple of rounds in the history. Then like you keep accumulate like along the history, um, how many tokens and how much attention like all these tokens paid attention to me in the history. And then like every time the lower token will be removed because like fewer and fewer people pay attention to you now, right? So the map here shows that basically the static sparsity versus the H2O says, oh, the blue ones are the ones that's immediately before myself. The green ones are the ones that I calculate with this heavy hitter, this H2O. With both of them, it's enough to give you very good accuracy, and their results actually confirmed that. So you can see that this static sparsity with H2O, you can keep the accuracy, while the static sparsity is not. There also like something that you need to pay attention is that, like this local window. Like in here, it shows a local window of two tokens before myself, right? But it's a designing choice. Okay. So next, so you have 50 minutes. I'm going to finish this LM serving systems. Um, so when we are trying to optimize, this large language model serving systems, all these, of course we talked about latency, we talked about, and accuracy and all that. But let's try to break down this a little bit. The first metrics we want to take a look at is the time to first token. So this is the pre-filling stage when you have the prompt go to the model and then it's coming out of the first token, right? So that's the TTFT. And then like it's the time per output token. So once you have the first token, now it becomes the prompt plus the first token, right? And then generate the second token, right? And that's the latency for every subsequent token needs that much of time, right? So that's the time per output token. So those are two different. So the whole latency equals to, the first token, the pre-filling stage, plus the time per token times how many tokens I have, right? So that's easy to understand. And the throughput essentially is the number of tokens um, um, per unit time. And the optimization goal and trade-off. And we want to minimize the time to sometimes, for example, when interaction is very important, you want to minimize the time to first token, right? Of course, you want to, maximize throughput, reduce the TPOT, and all that, and and also some other. Um, so there's always trade-off. Processing multiple queries in concurrently increases throughput, but extends the token the time per token for each user. So there's always like this trade-off. Other heuristics: output length, input length, model size. So so page attention is kind of a virtual memory idea. So remember, we talked about, I think I showed this image earlier. When we are doing the attention, like we need all this KV value, right? So, but this is a very large number, okay? And there it's going to causes this page fragments. What that means is this, okay? So for this particular query, okay, artificial intelligence um, um, is the future, okay? Um, so first of all, we do not know how many tokens is going to be generated, right? So we kind of like need to, we need the cache slot for the prompt for the current step and reserve some of them for the future. And also like we are going to because we never knew we never knew like how long this is going to be. We always reserve some of the slots, so that give you this space that's not used. And also like in the cache we also have some other requests. So between request B and request A, you also have this fragment memory. If learn operating system, this is a very easy to understand idea, right? So what they did essentially is doing this memory paging idea. Um, Memory management in the operating system. The process A is this and B has this. They say they do the same for the KV cache block. Okay, so they have this different blocks. They maintaining this page table, and for them they call this a block table. Essentially, each block is to a logical block is mapped to a physical block. That's what it is. Right? And therefore, when we have two requests, um, both of them can sharing the same physical block, but logically each of them it's this, and you don't need to reserve anything because it's more like on-demand request, right? And even more, you can actually share some of the common prompts. For example, like if you want this is the model, say, well, the future of cloud computing is, and give me three possible. If your prompt is this, this, okay, and give me three possible, scenarios. And then like for when the model is generating all these three different outputs, this part of the KV value, they are all shared, right? So they can be shared in the by using just pointing to the same memory block. See, so the sequence A can point into here, sequence B can also point to here. So they are sharing the same KV block. Okay, so that's like not very hard. So the real the flash attention is also very important optimization I want to talk about. So when we are doing the attention process, I show the equation over here, right? So if you think about it, when we are doing attention, the whole process goes like this. I am going to have a K I'm going to have a queue. I'm going to build up the map, right? The attention map. I'm going to do softmax. Okay. I'm going to multiply with the V, right? And the input is K and the Q. Okay. So the input is K and the Q. The output is V. Make sense? The the attention map essentially is an intermediate step. We don't really need it. I mean, by not needed, I mean like the output does not need it. We don't need this attention map. The only output we really care is K. Well, give KV, K and Q, give me the V, right? So that's the, and when you are calculating this matrix, because this is the n by n attention matrix, this intermediate step actually explodes. So this memory is like going to be huge, right? So flash attention basically is trying to reduce this attention map size. So the key idea is tiling. Instead of instead of calculating this whole KV attention map and calculate the V, I'm going to do the tile. So here, give you the idea is that I'm going to use a chop, small chop, and only calculate a small part. Okay, and then I'm going to multiply with the V and give you the result. But if you do this attention, what is the problem now? Anyone can help me here. If you're simply doing this, it's not, the math is not correct. Why? The math is not correct. Anyone know why? The math is not correct here. So remember, when you are KV attention, um, when you have this matrix, you have this block, right? And the most important thing is this softmax. The softmax essentially is trying to see like which tokens are more important, and then like multiply with the V, and right. So that's how we get the V. If you are doing this, only doing this block, let's say like this one, this Q multiply with this K, and you got this one, right? And you are directly using this to multiply with the V, which is not correct. Because I need to do softmax. But to do softmax, I need a what? I need the global value. Does that make sense? So do you remember like what's so this is the softmax equation. Okay. In order to do the softmax, I needed to know the global maximum number for this entire row. So I can calculate the softmax for all this, for the whole column. Does that make sense? But now, if you are only doing this one block at a time and just directly multiply with this V and store it here, the softmax is gone. Make sense? So therefore, the key problem flash attention is trying to solve is this softmax problem. So it does is this something called an online softmax. Okay, so here the step. The GPU loads block 1 into SRAM and find the local maximum so far. Okay, what I have seen so far. So this is like a bubble search kind of thing. So far, for all the KV values I see, the maximum is M1. So I'm going to calculate the softmax just based on this single number. Okay, but we know that this number is not correct. But that's fine. I'm going to just use this as for now. And then when I'm proceeding to the second block, okay, I find the local maximum number and compare with them and find the new one. If if the older one is still the maximum, so far we are still good. Okay. But if the new M2 is the maximum number, they do some correction. They do some correction. So mathematically, you can correct the older sum by simply multiplying difference in the exponents. Okay. So the different they basically they are going to correct the older value with this. Okay, and then like using this correction to update the final output. So by doing this, essentially you are doing progressively calculate the soft max and keep correcting it to give you the final correct v value. And this is a significant because now I don't have this, huge matrix, and the huge mix means that like memory loading latency and all that. That's why it's called this flash attention. It significantly improves the computation latency. Now the bottleneck is totally reduced from the memory access and it's purely just on the computation. Okay. So this is the flash attention and see how it's, give you this speed up. Speculative attention is also very interesting. So let me explain this. So basically, I'm going to have a smaller model and have a large model. The smaller model is autoregressive. It's slow, right? So start, so the smaller model is going to do this. Several famous songs are. So it's an autoregressive process, means that the smaller model is executed over and over again. But because this is a smaller model, it's going to be fast. Okay. Then once you have a draft, several famous songs are, I'm going to feed it to the large language model simultaneously. And this is not regressive. It's all everything in parallel. So the large model only need to execute once. Okay. And then because I already have the draft, everything, right? I'm just going to generate, this verification. So several famous songs are. So basically says, oh, I'm going to verify the student. Let's say this is the student, not really student. The small model output is the same as what I generate. If they are the same, so we only need to do autoregressive many times for small model and do verification once for the large model. So that improves the latency, right? So you are doing this over and over again. So basically, if the green, it's green means that I'm going to accept the draft. If it's not, I'm going to reject it and ask you to regenerate this. Okay, and blue one is the correction. So by doing this, you can do 2 to 3 times speed up. So final, it's the batching. So running multiple inputs simultaneously maximize the throughput, especially in the server when like we have many people sending requests at the same time. If you don't have any batching, then like each batch is processed individually. Static batching is like, I just wait for a full batch before processing. Can be processed offline. Dynamic batching, batches are processed when full or after a set time of delay. And this continuous batching. And let me use image to show you the idea. So this one give you better illustration. So when I have many requests that come into my system, let's say like cloud server, dynamic batching basically is like a bus. Okay, I'm going to get off at the different stops, and oh no, I'm sorry. Dynamic batching is this a bus leaves when full or after a time expires. That's how bus works, right? Ensuring minimum waiting time. So when the new thing come and either my bus is full or the time has already arrived, so the bus has to leave. So in this continuous batching, it's more like a bus where passenger get off at different stops, making space for a new rider. So just keep every time you finish one token, then I'm going to get one token, keep feeding the space. Okay, so So far, um, this Tensor RTLM is this state-of-the-art large language model serving infrastructure from NVIDIA. Okay. And let's see, like all these topics, the key features we have covered in this class. We covered the multi-head attention. We covered the multi-query attention, group-based query attention. We talked about this in-flight batching. We talked about paged KV cache. We talked about W4 A16, W8 A16. We talked about smooth quant, GPTQ, AWQ, floating point 8. We talked about the rotatory positioning and coding. We are going to introduce this tensor and this parallelism probably in the future when the time is. So all the topics we covered so far covers all this status the SOTA infrastructure ideas. So they are truly used in the industry. Okay. So summary for today's class, we talk about quantization, pruning, serving, and all that. So next lecture that's after spring break, we are going to talk about the long context. Means that how do you keep increasing the context length so that the model can remember more of the history of your conversation. Okay. All right. That's all for today, class. Thank you very much.